We've all learned in high school that the equation x squared plus 1 equals 0 has no solution, since the evaluation of the equation gives us x squared equal to -1, and we cannot take the square root of negative numbers, so the equation has no solution, right? Actually not. With a field known as complex analysis, or complex numbers in more general, the shown equation actually evaluates to I, the standard unit of imaginary numbers, and it is defined as the square root of -1. This actually gives us a solution, although it's no real solution, but an imaginary solution instead. The shown example gives us a definition for imaginary numbers in a more general way, but imaginary numbers seem like a thing only pure mathematicians care about. But the field of complex analysis, so the study of complex numbers, actually finds many applications in other fields of math, like number theory, but also in fields of electrical engineering, physics, and hydrodynamics. The rapid growing interest in complex analysis made it into a very important branch of mathematics, followed from the roots by mathematicians like Leonhard Euler to the increasing study of this branch of math all around the world. Leonhard Euler, the famous mathematician who also developed E, which we talked about in the last video, also developed one of the most beautiful equations of math, which we also discussed in the series of complex analysis as e to the I pi plus 1 equals 0. This relation seems completely odd because it combines concepts from a lot of different categories like geometry but also analysis. But with a good understanding in the ground rules of complex analysis and complex numbers, and with a little background in things like geometry and calculus, we can easily figure out what this equation really means. And in today's lecture we're going to set the start by learning about complex numbers and the representation of them in the xy plane, which both stay at the very roots of complex analysis. As discussed earlier, we define I, so the unit of imaginary numbers, as the square root of -1. This gives us the general definition that negative numbers like -2, -3, or even -pi all have imaginary square roots. This means that the equation x squared plus pi equal to 0, for example, now has two possible roots: I times the square root of pi and -I times the square root of pi. The difference to real numbers is that the complex or imaginary numbers lie within a separate dimension to the real number line. So if we imagine a normal number line with all the real numbers, the imaginary number line lies perpendicular to the real number line. This just means that we can describe complex numbers such as a plus bi, where we have a real part and an imaginary part multiplied by a real number, as a point on a plane, represented with the point P, A, and B, with both coordinates as real numbers. This plane is usually referred to as the complex plane, and the x-axis is the so-called real axis and the y-axis is the so-called imaginary axis. If both a and b, so both real parts of a complex number, are 0, the point in the plane is just the imaginary number, or the complex number, z equal to 0, otherwise referred to as the origin. We can change both a and b to any real numbers such that we can identify and justify points as, for example, p21 as 2 plus I. Represented with a vector, we can see that we move 2 units on the real axis and then 1 unit at the imaginary axis. Another example would be the point 3 and -1 as 3 minus 2 times I, where we move 3 units on the real axis and -2 units on the imaginary axis. This shows the direct correspondence of imaginary numbers to real numbers, and we can also see that we can represent a complex number as a vector in the xy plane. A reasonable question to ask is, what will happen if we add both terms of the complex numbers? So we add 2 plus I plus 3 minus 2i. As the rules of complex numbers and complex addition and subtraction do apply, which are basically just the same as for vector addition or general addition on the real number line, we can just add the real and the imaginary part algebraically, so we get 5 minus 1 times I. And where does this point sit on the complex plane? Right, directly at the point 5, negative 1. And maybe, but just maybe, you can see a little visual meaning behind this. I give you a little pause and ponder time here. The addition of complex numbers, so a number with both real and imaginary units, can be represented as the addition of two vectors in the xy plane by using the rules of parallel displacement of vectors. To be all clear, with the addition of two complex numbers, so with the addition of two numbers who both have an imaginary and a real part, we do nothing else but simply add their different components. This gives us the right to treat them as a two-dimensional vector, where we move along the first path and then move along the second path in order to result with a final path, an addition of two complex numbers. The shown examples of addition gives complex numbers the feature of addition and vector addition, just like in a two-dimensional coordinate system. Since this isn't really separating the complex numbers from two-dimensional vector spaces, we surely look at multiplication to fully understand the separation. This only works because complex numbers are a two-dimensional system with the idea of multiplication behind them. And as in nearly all of math, everything works better with an example. So let's take a look at the multiplication of 2 plus I times I, which is 2 right, 1 up, times 1 up. If we solve this algebraically, the 2i go together and the I squared becomes a minus 1, so we get minus 1 plus 2i since its definition allow it. If we graph the number as a vector on the complex plane, I want you to notice something. The new negative 1 plus 2i and the 2 plus I have a 90-degree angle between them. But why is that even interesting? Let's take a look at the number 1. If we multiply 1 by I, it becomes 1i or I, which also lies 90 degrees away from its original point. Both vectors also always stay the same distance away from the origin. In other words, they still have the same modulus. Let's make this more clear by looking at a more narrow point on the complex plane and draw a unit circle. This is just a circle with radius 1 away from the origin. Let's also mark one point on this unit circle, which also now has modulus 1. How can we deal with complex numbers on the unit circle in the complex plane? With a little background in trigonometry, we can do a little triangle with an angle of alpha. And since this is a right triangle, we can also define the lengths of both missing sides by sine of alpha and by cosine of alpha. The interesting part is that we can describe both the real and the imaginary part of the complex number as a combination of trig functions, and that this works for every point on the unit circle. So for the unit circle, we can define a complex number as cosine of alpha plus I sine of alpha. To now get clear what it means to multiply two complex numbers, let's add another angle, so-called beta, so we get cosine of alpha plus I times sine of alpha times cosine of beta plus I sine of beta. If we multiply that out, we get a pretty long expression. But since this is just trigonometry, we can also apply trigonometric rules. From this we get cosine of alpha plus beta plus I times sine of alpha plus beta. What this says is that if we multiply two complex numbers with an angle of alpha and beta, they result in a new complex number with angle alpha plus angle beta. What is so interesting about this is that when we multiply a complex number, it is the same as just rotating around the unit circle. This means that complex multiplication is directly linked with general rotation. In a more general sense, this means that rotation by a given angle theta is just cosine of theta plus I sine of theta. This means that we can describe any complex number on the unit circle as a combination of cosine of theta plus I sine of theta, which is given by the multiplication of the angle theta. And for the trig lovers under us, it is beautiful to see how these numbers relate to simple trigonometric rules and how they can describe by the addition of trig functions. Okay, now we know what it means to multiplicate by I because it gives us a 90-degree rotation. But what is with the multiplication of real numbers? Let's for example take 1 plus I times 2. So a complex number times 2. We can graph both numbers as so. Algebraically, this multiplication gives us 2 plus 2i, since it just doubles each component of the complex number. Graphically, this is just like 1 plus 1i, but just stretching its length out. From this we can conclude that multiplication by a real number just has the effect of stretching the original number. Putting these things together allows us to describe any complex number as a combination of trigonometric functions with the help of the given radius. This means that we can take a look at any point in the complex plane and describe it as a combination of such trigonometric identities. We have now defined several ways to define and show complex numbers, including the algebraic interpretation, the point on the complex plane, a vectorial representation, and the trigonometric interpretation, also known as the polar form of complex numbers. But more on that on another time. To finish today's lecture, I want to discuss what is known as the modulus, or the absolute value of complex numbers. If you remember the famous law of a squared plus b squared equal to c squared, you already know everything to compute the absolute value of any complex number. But to step back a little, let's take a look again on what the Pythagorean theorem actually implies. It says that for any triangle, given that is a right triangle so that it has an angle of 90 degrees, the square root of both shorter sides results in the square of the hypotenuse. So to find out the length of the hypotenuse, all you have to do is to take the square root of the result. The shown animation given by the fabulous animator Mathematical Visual Proofs on YouTube gives a great insight on how this actually works by just shifting around the different shapes. If you have any background with basic linear algebra, you probably know that you can describe the absolute value of a vector, in other words the distance of a vector, by computing the Pythagorean theorem on the components of the vector. For a vector given its x component being 3 and its y component being 4, the length of it comes out to be 5, which is also known as the famous 3, 4, 5 Pythagorean triple. If we take this a step further and go back to the vectorial representation of complex numbers sitting on the complex plane, we can see that the length of the vector always identifies as the distance from the origin, since the vector of any given complex number starts always at the origin. For any of you already waiting for me to reveal it, I admit that this next part is quite pleasing. Given the two components of any complex number, we can identify its modulus, which also gives us the radius we talked about earlier, since the radius of any circle always describes the distance from the center of the circle, which sits at the origin to the edge of the circle. Thank you all for watching today's math lesson. This was part 1 of the complex analysis series, giving a little introduction to what complex numbers are and how they behave on the complex plane. For episode 1, I think we have covered a lot of the basics. We will continue as soon as possible with more details on complex numbers such as Euler's identity and more ground rules before stepping in the fields of complex differentiation, integration and more. For now, I hope you have enjoyed this episode and I'm looking forward to seeing you soon.